This PhysCast looks at a particle interacting with a step potential. Pause the video and read through the problem carefully. In this question, we have a step potential, that is, an abruptly changing potential energy function. So we might think about that as a potential that is zero for some region of space, then has an abrupt change, and then continues along at some other constant level. We were told that this initial one is zero in energy, and that there's a change, a step height here, that actually has an energy of 65 electron volts. And there's a particle, in this case a proton, that's moving toward this potential step, and it has a total energy, we're told here, slightly higher than the step, in this case 70 electron volts. And in the first part of the problem, we're being asked to think about the wavelength of that electron in both sides of that potential step. So we might remember that we could think about the wavelength here in terms of a wave number k. K here is simply 2 pi divided by the wavelength. And so we might like to think about region 1 being on one side of the step and region 2 being on the other side of the step. And it turns out we can write this k value in terms of the quantities in our problem here. And you might want to check that this makes sense. It's going to be twice the mass of the particle multiplied by the total energy minus the potential energy, the difference between those two, and divide that by Planck's constant squared, h bar squared I should say, and of course it's the square root of that entire thing. So that's an expression that we should know for the wave number of our particle, and we can think about now, perhaps we'll calculate K2 first up. That might be interesting for us to do. We were simply going to put in the values we have given to us in the problem. It's a proton, so twice the mass will be twice 1.67 times 10 to the minus 27 in SI units, and then we're going to multiply that by the difference between the total energy and the potential energy, and in region 2 that would be 70 electron volts minus 65 electron volts, and we'll convert that to joules by multiplying by 1.6 by 10 to the minus 19, and we're going to take the square root of all of that, and then we're going to divide by, up here, the square root of h bar squared. That will just be h bar, which we can write in SI units as 1.05 by 10 to the minus 34 in joule seconds. And when you do that calculation, and you should take care when you're doing calculations with these various numbers in here, we'll get a number here for K2, the wave number in region 2 there, of 4.92 times 10 to the power of 11. Of course, we better give that some units. That will be an inverse length here, so we've done everything in SI units. That will be in meters to the minus 1. And then the question really asked for the wavelength. This is the wavelength in region 2 here, the wavelength after the particle has gone over that step potential there. And so that's going to be, of course, 2 pi divided by this 4.92 times 10 to the power of 11, and that will give us a wavelength in that region there of 1.27 times 10 to the minus 11 meters. So there's the wavelength there on the high side of that potential step. And you might not be completely surprised if you've done other calculations here. A wavelength this small, kind of down in the 10 to the minus 11 meter range, is not particularly unexpected for a proton moving along. And we can do exactly the same kind of calculation to figure out the value of K1, the wave number in region 1. And in fact, I won't bother writing it out in great detail. You should try it yourself. But you can see the only thing that's going to change between the calculation of K2 and the calculation of K1 is this E minus V factor in here, the total energy minus the potential energy. And in fact, when we do this calculation for K1, this minus 65 shouldn't be there because 65 electron volts isn't the potential energy in region 1. That actually should be 0 in there. So we can essentially repeat the details of that calculation, but instead of multiplying 70 minus 65 in there, we'll just multiply by 70 minus 0. And if you do that calculation, and you might like to pause the video and actually do that calculation yourself, you'll wind up with a number here for K1, the wave number in region 1, of 1.84 multiplied by 10 to the 12, and that will also be in inverse meters. And then when we calculate the wavelength that corresponds to that wave number in region 1, that is 2 pi divided by that value there, we'll wind up with a wavelength there of 3.4 by 10 to the minus 12 meters. And you can see the wavelength in region 1 is smaller than the wavelength in region 2, and that should actually make sense. We know that as this particle goes over the step, if indeed it does do that, it will wind up with less momentum in region 2. Okay, so it'll have some of its kinetic energy taken up by potential energy, so it will certainly be moving more slowly. It would have a smaller momentum, and a smaller momentum corresponds to a larger wavelength. So there's a larger wavelength in region 2 than there is in region 1. Of course, they're both very small numbers here, but certainly as the wavelength increases as the momentum decreases in our system. So let's look at part B of this problem here, where we're trying to calculate the probability of this particle reflecting off this potential step. And if you go back through the working in lectures or in a textbook for what is the reflection and transmission coefficients for this kind of problem, where we deal with the wave solutions to the Schrödinger equation on both sides of the step, and then we match them at the step, we find we wind up with a relationship for example, the reflection coefficient here, capital R, simply to do with those wave numbers K1 minus K2 divided by K1 plus K2, and we square that entire ratio there. And so fortunately we actually did calculate those values of K already in part A, so we can just use them quite directly here. In fact, to make it a bit simpler, I might change my expression for K1 here to put it in the same kind of units as I have for K2. I can make that 18.4 times 10 to the 11 inverse meters, and then I've got everything for K1 and K2 both in this unit of 10 to the 11 inverse meters, and I don't have to worry about writing that unit in here because it will just cancel top and bottom because this is a ratio. So then K1 minus K2 will just be 18.4 minus 4.92, and divided by the sum of those, 18.4 plus 4.92, and then I better square all of that. When I do that, I find the value I get there is 0.33, or 33% if you prefer. So the probability that this proton will be reflected as it encounters this potential step is actually pretty much a third, 33%. And you might recall that's quite different to what a classical expectation would be. If this particle has energy higher than the step, classically we'd expect no reflection. This particle would definitely go over that potential step. But when we remember that particle also has wave-like properties, and we have to think about what a wave would do when it encounters some abrupt change as it's traveling along, there's always some likelihood, some non-zero probability of reflection there, and that's what we're really seeing here in the quantum mechanical treatment of this particle interacting, this proton interacting with the step here. And for these particular conditions, it's actually 1/3 likely to reflect, or if you prefer, if we had a beam of protons coming along here all with this energy, basically 1/3 of those protons in the beam would be reflected and 2/3 would be transmitted.